Okay, please, if you see something which I did not clearly stated, say it. Raise your hand and say it. Sometimes there are a lot of information and I miss maybe I forget to mention a few things. So someone asked me during the break, why is the pictures as shown here, which are like not symmetric? You see the flame is basically symmetric with respect to the axis. Well, it is. We have plotted just here half of the, of the tube. It goes from 0 to 1. It should go to -1. So this flame is curved like this and so on, right? I forgot to mention that, but so same thing here. It's a curved flame like this. This is, in other words, half of the picture. And we assumed symmetry. By the way, that's not necessarily so. You can have a flame propagating in tubes that are not symmetric. They are off due to various other mechanisms. So, okay. So the next item that I want to discuss, it's related to ignition. And I am first making some general statement, which are mostly phenomenological, that appeared in the literature from many years already. The first one is the idea of a minimum ignition energy. So if you deposit locally in a homogeneous mixture a kernel of heat, ignition will occur only if the amount of energy exceeds some minimum energy, clearly. In other words, if you put in some heat locally in this region at time t equal to t0, if the amount of energy is below the minimum, then by conduction heat will be spread and no explosion would happen or no ignition would happen. But if the energy is sufficiently large such that the temperature is perhaps close to or slightly bigger than the adiabatic temperature, then clearly a flame can propagate at the speed of the laminar flame speed. And so the anticipation is that the minimum ignition energy will be the volume, right, which is rho u times the flame thickness cube, multiplied by the difference in enthalpy between adiabatic and the cold temperature. So this is a phenomenological expression, but that's what is roughly expected. And one find that experimentally, indeed, the minimum ignition energy correlate well with the quenching distance cube. We talked about the quenching distance before. Therefore, you can make a simple argument that the minimum energy will be inversely proportional to the laminar flame speed cube, as these experimental curves show, that mixtures that are more reactive require a smaller ignition energy, right? So I mean, you see that for different mixture and the amount of minimum energy is usually lowest near equivalence ratio 1 and so on. Okay, and the other thing is you can also relate this to, I'm not spending too much time on this because you can find that in basically every book and it's all phenomenological. You can also see the dependence on the pressure. So of course the reduction in flame speed seems to facilitate ignition, but on the other hand, which is what you will expect because the flame speed usually decreases with pressure. But on the other hand, the flame thickness has the opposite effect, and so there is a there is a sort of a, I'm sorry, the density here has an opposite effect. And see, the density rho u gives you a p to the 1, and the rest here, LF cube, is proportional to SL minus 3, and so that gives you this part, the negative part in the exponent. So on one hand, reduction in flame thickness facilitate ignition, but then if you increase, it will increase in mixture which are more dense, right? So these are some general comments. Oh, the last one is that you can also see how an inert can affect the minimum ignition energy, because inert essentially is related to the thermal diffusivity, right? You increase the inert, that's what determines mostly the thermal diffusivity of that mixture, and that affects the minimum energy. Okay, and of course all these arguments are based on a simple argument that are related to the thermal theory of flames, but the chemical kinetics and chemistry could affect all these things in a more complex way, and I cannot tell you more about this. So thermal explosion, and that's what I want to focus on. Thermal explosion is similar to ignition, really. Thermal explosion, usually we think of something big, but a local thermal explosion is an ignition. And the important question that we want to address are the criteria that predict whether explosion would occur or not. In other words, whether ignition would occur or not. The delay time, or the thermal induction period before something occurred that you can identify as an ignition, and to some extent, if possible, time history of the explosion event. So we're going to touch on all these questions, and we will start with the simplest theory, which is due to Semenov, and Semenov theory, and first adiabatic and then non-adiabatic. So first, suppose that you have a homogeneous combustible mixture in some vessel, and there is no diffusion, heat conduction, and so on. Everything is homogeneous. So we can write the conservation equation, mass and energy, right? So now the energy equation is written here, but note that there is a CV, not a CP, because it's a constant volume, and so what we're writing is essentially the internal energy variation. And it's equal to the rate of the reaction, assuming that Y is the species or the reactant which is being consumed, Q is the heat release, B, as before, is the pre-exponential factor. And this is the mass consumption of the species Y. And so initially, we start with a certain amount of reactant, Y naught, and temperature T naught, and we ask when would that explode, right? Okay, so this is a very simple one-dimensional system of equation. You would expect a quick analytical answer. Well, there is one, but it's not very useful, as you see in a minute. But the first thing you can immediately see is that, of course, if you add the two equations, you can find a quantity which is conserved, which is in fact more or less the total energy or the total internal energy. Since this is equal to 0, then you know the value from the initial condition, and so you first of all find that there is a relation between Y and T, so you don't need to solve for both, right? And the second thing is, if you evaluate the constant when Y is 0, namely when everything is consumed, then you obtain the final temperature, which is like the adiabatic temperature at constant volume. I already talked about that before, and it's the same expression. Okay, not the adiabatic flame temperature, the isobaric one, but this is on constant volume, and so it's divided by CV. Okay, So if that is the case, then we can substitute into the equation for the temperature, and we have a single equation to solve, highly nonlinear, but first order. So first order, you can immediately, it's a separable equation. You see the right-hand side depend only on t, so you can write dt divided by the right-hand side equal to d little t, and then integrate. And so you get some integrals which are known as the integral function, but it's not very illuminating to look at that analytical solution. So we want to find something a little simpler to understand what's going on. And so again, we want to use the idea of beta naught, the activation energy parameter, being large. So if beta naught is large, then what you will see is that they would take quite a bit of time until something happened, and then something would abruptly, or the temperature would abruptly jump towards the equilibrium temperature. If beta naught is not large, the transition is rather slow, okay? And of course, this is more realistic for combustion system, and also it illustrates something quite interesting, that, I mean, if beta naught is finite, how do you define when ignition occurs? It's totally arbitrary. You can define it where the slope is this or that, but it's a choice that you make, and it's not a unique choice. On the other hand, asymptotically, you're going to see that we can identify this red line without any arbitrariness. So the idea is that, after all, ignition is an asymptotic concept, okay? And that's what you'll see in a minute. So we go back to the equation, and since beta naught is large, as we have actually seen from this is the numerical integration for different values of beta, by the way. As you see here, when beta is large, the temperature in the beginning doesn't change very much. And so what we are going to assume is the temperature doesn't change very much from 1. So it's 1 plus a perturbation, and phi of t is the perturbation. So if we substitute into the equation, we get an equation d phi dt is q e to the phi. Phi at 0 is 0 because the perturbation initially is 0, the temperature is 1. And when you integrate that, you get phi equal to minus the log of 1 minus qt. Okay, so here is the temperature T naught, that's essentially T. So I plotted here 1 plus the beta naught to the minus 1 phi, and where the logarithmic become, or when time T is 1 over Q, that's when the log become infinite, and so you have a clear definition of your ignition temperature. So the temperature, the ignition temperature, you can write it now explicitly in terms of the physical variables, and you see it depend on inversely on the amount of heat release. More heat release, the shorter the ignition time, that's clear. More fuel you put in, the shorter the ignition time. And if the reaction is fast, the shorter the ignition time, okay? But CV will be working in the other direction. In other words, larger CV will cause a larger T ignition, and so on. Okay, so this is the first thing that you can draw from simple Semenov theory, and this was for the adiabatic case. The second case I want to deal with is the non-adiabatic. So if you have non-adiabatic, to the energy equation we add a heat loss. Again, it's a phenomenological heat loss, so that if you have a vessel, the heat loss is going to be proportional to the surface area of the vessel, multiplied by some K that depend, let's say, on the material that the walls are made, the T minus T naught. Since everything in this equation is per unit volume, so is that term divided by the volume V. And of course, to this one have to add the species equation, or the consumption of the reactant. But in this simple theory, we're assuming that during that event of ignition, very small amount of reactant is being consumed. There have been in the literature paper that have accounted for later on for the consumption of the fuel, but it's nicer, at least for this presentation, to look at the simpler case. So assuming that y is approximately 1, it doesn't vary much. And so the only equation that I want to focus on is the temperature equation, which if I scale the time with respect to the conduction time, which is defined here, then you get an equation that has one coefficient, one parameter only apart from the activation energy, which is D. And D is essentially written here is proportional to delta with the exponential due to the Arrhenius. And what is more important is really delta. And delta has the product of the heat release multiplied by the ratio, conduction time to reaction time. That's an important ratio, okay? Conduction time to reaction time. Now, so D effectively is this ratio, the ratio of conduction time to the reaction time. And the last term is the heat loss, right? And we start at initially at T0 equal to 1. Of course, in principle, we want to solve this equation in time, but I want to look at some features of that equation before actually talking about its solution. And the features are the following. The question that I ask is, are there any other equilibrium, or are there any equilibrium solution to that equation? Equilibrium means that nothing changes in time, so the right-hand side vanish. In other words, the production or the chemical reaction balance the heat loss, okay? Are there such situations? So, well, here is the production term, and then is the heat loss. The only thing I did, I moved the D from here to the denominator just for, it's simpler to examine it, the equation this way. This is what I'm doing, if these two terms can be balanced. And the answer is, well, let's graph it. It's a graphic method. So first of all, I graph the exponential, and that's this red curve here. You see when it goes to 0, when t goes to infinity, of course, or I'm sorry, it goes to, no, it goes to, when t goes to 0, yeah, e to the negative infinity goes to 0, that's correct. So e to the negative, when t, yeah, it goes to 0, that's fine. And then there is, the upper part doesn't really interest me much, it's only this part of the curve. And then on the right-hand side, it is a straight line with a slope 1 over d, like this line here, right? So do they intersect? Is there a steady, an equilibrium? Well, yes, as long as the slope is large enough. It has to be when it becomes small enough, and then it's going to be tangent to the curve, and when it's smaller, it will never intersect. It will intersect with this part of the curve, but that's not of interest because it's at high temperature. So, so there is an intersection of the two curves only when d is, should be bigger than. B is d, oh no, I'm sorry, 1 over d is the slope, so it's correct. So when d is less than d critical. And then the temperature here is T critical. So all this can be easily done because we can, in other words, to find the critical value, because it's the point where the slope of this is equal to the slope of this. And so when we compute the slope, what we obtain is that there is such a point. So here is what happens. When D1 is less than D critical, meaning there is a steady state like the blue curve, right? Then the temperature will increase, eventually will reach that steady state. Steady state, it's T1, which is this temperature here, right? Okay? This is just a graph of the left and right hand side, and this is graph of the temperature as a function of time. So as a function of time, temperature increases and reaches steady state. What happens if you are, the slope, 1 over d, is smaller than 1 over d critical, or when d is bigger than d critical? Well, eventually the reaction is generated, or energy is generated at a rate which is much larger than it can dissipate at the wall, and so it will explode. And so as a function of time, you're going to get a curve that increases up to a certain point, then it will explode, right? This is like your ignition temperature. Okay, so this is, or sometimes it's referred to as thermal runaway or blowout at a finite time. Okay, so, and this is the critical values. I thought that this should have appeared before the other graph, but doesn't matter. So to obtain the critical value, you say that the heat generated is balanced by the heat loss, and the derivatives at this point are the same. In other words, the rates are the same. And so you can, you have two unknowns, which is D and the critical temperature, and you obtain them algebraically from here. It's a very simple solution. And if you want to use the activation energy being large, then you obtain a simpler version of those, but those are already, you know, analytical expression that can be used. So it's no, nothing, it's straightforward. The key point of all this is now if I rewrite the expression in a dimensional form, remember that D was related to the, in fact, it has in it all the parameters, the conduction time, the reaction time, and the heat release. Then clearly what you obtain is condition at criticality. So at criticality, here is the expression that I just wrote before, the D critical expressed in dimensional form. And so you can identify the critical pressure before ignition, before explosion. You can identify the critical mass needed for explosion and so on. Okay? A classical example that I give in classroom is you have a pile of hay, and it's a cube sitting on the, say, on the floor or somewhere at some temperature, and you determine how long it will take for this to explode due to some initiation of some reaction that can develop there. And so you have to determine the surface area, the volume, blah, 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 and determine the condition, so on. So you can obtain anything you want from here. Okay, so this is, if you want to estimate the induction time, which is this curve here, oops, which is the time it took here for explosion, okay? You can estimate it if you use this idea of large activation energy, because it will give you then a simple expression for the time it takes for explosion to occur. Okay, I'm not going to go through this, it's a detail. The next step in the theory, it's Frank-Kamenetsky. Frank-Kamenetsky theory is, okay, you want to take into, it's no longer a homogeneous system, but you allow for diffusion. Again, Frank-Kamenetsky only focused on the temperature, assuming that the consumption is minimal and it's not affecting the explosion conditions. And you rewrite now the energy equation, but you allow for heat conduction. And at the wall, you assume that the temperature is given. If you want to change that to incorporate also heat losses at the wall, it's doable. I think some of that has been done in the literature. And there is a variety of really interest in that subject, not only strictly speaking in combustion. So I have seen many applications in other things as well. Okay, so if you write now the dimensionless form of this equation, now there is this delta parameter that appears similar to the d before, and in fact in the literature is known as the Frank-Kamenetsky constant. And so again, it's a ratio of the conduction time to the reaction time, basically. Okay, and so now you have dt by dt, the time rate of change, heat conduction, and heat production. And at the wall, temperature is scaled, so it's 1. So the first question I'm going to ask follow the same idea or the same trend that I presented up to now. Are there any steady states? Because we know if there are steady state, eventually heat gets generated but also dissipated until the steady state is reached. If there is no steady state, then heat is generated at a rate which is larger than what it gets dissipated and explosion occurs. So those are the critical conditions that we want to find. And so the question is there a balance between heat conduction and heat generation? But now it's no longer an algebraic equation, but we have to solve Laplacian of t equal to this. And Frank-Kamenetsky used exactly that idea, this approximation that beta is large. And in other words, he linearized the exponential or rewrote it as we are used by now as e to the phi, right? When beta is large, you can rewrite the exponent in that way. So the whole problem is only solving this equation with only one parameter delta, right? You can in principle solve it for any geometry you want, and the natural geometry that people have solved them is a slab, a cylinder, a sphere. And then I was once in a mathematical conference, and someone say, well, let's assume that an elephant is a sphere. So you can always have to assume your geometry has a certain shape that you would like. So here are the solutions known for the critical condition for a slab, for a cylinder, and for a sphere. Interestingly, and it's taken from a book by Aris, well-known chemical engineer, it's interesting that the slab you can get an almost analytical solution, by the fact that it's the simplest. For the cylinder, you can get a closed form solution. For the sphere, you do not, and in fact, there are multiple solutions. As you see here, it keep on turning back and forth. But for our interest, it's only the first critical condition which counts. In other words, what we have here is the maximum temperature as a function of delta. Maximum temperature presumably would occur at the center if the losses to the wall is a constant. Otherwise, it can happen elsewhere. And when I say there is quite a bit of literature on this, a lot of the discussion are what if one of the a section of the wall is heated and not the other part. So clearly ignition would happen in that end, and so that changes the result in a certain way. But if not, it happened at the center, and so the maximum temperature would increase until explosion, will enter. So those are the three numbers here for these three conditions, and from that you can determine the critical volume, the critical size, the critical pressure, whatever you want. I think, there is one more here. I also found this curve interesting, which is the critical delta C as a function of the BO number. The BO number is essentially the extent of loss at the wall. So if the wall is not assumed to be a constant, but there is a degree of loss, then clearly the critical one will be a little less than what we have. but the results are such that they asymptote to the 3 constants that we have seen before. Okay, I think that's the last thing, and then I want to move on to my although it's one of the interesting topics that I particularly want to talk about. In fact, it's going to start today and the rest will be tomorrow. It's at multidimensional, time-dependent, if you like, flames. So flames are no longer planar and where hydrodynamic effects come into play. And today we're going to talk about the simple theory, and tomorrow we'll talk about the effect of stretch and Lewis number. I'm going to start with the first part, and then we'll take a break after the first part. And yes? Can you speak a little loud?
So the ignition delay that you got from the Frank-Kamenetsky theory, how far does it deviate from the quoted literature values, like in terms of auto ignition delay?
Well, you're talking about very specific cases now. What we are talking about an ignition delay in a homogeneous system. In a homogeneous system, these values turn out to be, they correlate well with what you obtain if you do an experiment of this kind. It's people talk about ignition delay in various contexts, and obviously the term doesn't mean that it's identical to what we have presented here, right? But some of the feature here could be applied to maybe determine some of the things that you're talking about. The first thing I want to talk about is, in fact, something I added in this lecture here is hydrodynamic effect, but small scale. Small scale comparable to the flame thickness, and later I will talk about large scale compared to the flame thickness. Obviously, if you want to ask me what happened in between, I don't know. I don't know, meaning that most of the results have to be obtained computationally because you cannot extract from the change in scale sufficient results that are simple or in the version that I will show you now. So the small scale comparable to the flame thickness I will discuss of flame propagation essentially in tubes. So here is a long tube filled with unburned gas, and we ignite the mixture at some point, and we let the flame propagate. So and some of these results will be computationally or numerically, and we are not concerned about the ignition event. In other words, when we ignite the flame, it's like we put a planar flame at T equal to 0 that exists already and can propagate. Of course, ignition is important, but it's a different problem. I'm going to use the fact that the flame, that the tube is long, but the depth between the two plates is rather small, h, or at least it's small compared to the flame thickness. Now, this is a bit extreme because, well, if it's adiabatic, it's not a problem because the flame would propagate no matter how small the channel or the h is. But if it's not adiabatic, then the flame cannot propagate in channels or tubes that are very narrow. So first of all, I am not going to discuss the non-adiabatic. Yes?
Wouldn't there be a boundary layer effect on as the flame propagates?
Yeah, but we're going to have a full viscous region, so that will account for that. Right, otherwise you would. So if the channel was wider, you're going to have boundary layers and maybe a region in the center where, but as you'll see in a minute, what we're going to get is Poiseuille flow in the, so it's fully viscous. But now I want to also say that sometimes mathematically the structure of the solution extracted in a certain limit is very illuminating, is useful, and sometimes it's even true for larger values, although a priori you don't know that. So you have to do then numerical computation, but that helps to guide the research. So this is the important parameter that we are going to use. H over LF is small, A. In fact, I'm going to show you a result with A order 1 later on. But first, I want to extract that because you will see how nice the result come to be. So we are going to scale here the length with respect to the flame thickness because that's what's relevant in the longitudinal direction. The width with respect to H. And of course, the time will be related to the laminar flame speed. The axial velocity will be scaled with the laminar flame speed, as you expect. But V must be scaled with ASL, otherwise you cannot conserve mass. That simply come from the continuity equation. If Y is scaled with H, then the velocity in that direction must be scaled appropriately. Otherwise, you get a one-dimensional flow, which is not what we want. The densities and the pressure are scaled as they should, temperature with the cold temperature, and so on. So this is what you have, and now the tube can be closed at one end, open in both ends, close at the other end. So you have a variety of situations. We're going to see what happened. So what is the boundary condition at the end? Well, if the tube is open at both ends, you expect that the pressure should be the atmospheric pressure. So this little p is in my momentum equation should go to 0. Because remember, we are in the 0 Mach number limit. You have the ambient pressure P is taken out, and the P in the momentum equation is the deviation from the ambient pressure, or the dynamic pressure, if you like. If the channel is closed, then U will be 0 either here or here, right? Okay, so here we write the equation in 2 dimensions, time dependent, depend on X and Y. These are the full equation. No simplification except the 0 Mach number approximation. You have the Prandtl number of the viscous terms. You have the temperature equation, heat release parameter, and the species or the reactant which is consumed. And that's a mistake. Rho T is 1 and not 0, of course. Okay? This is one of the problems of computers, that you cut and paste. Because you cut and paste and you forget to fix the the errors that you have. Okay, so if A is small, remember that A is the parameter that I told you before, going to use small, then look what happened. In the continuity equation, there is no A, so the full equation is retained. In the momentum equation, when A is small, you must have a balance between the axial pressure gradient and the viscous term, the second derivative of U is Y. And the third equation just tells you that dP dy is 0. If anyone is familiar with lubrication theory, that's exactly what you do in lubrication, or thin film theory in fluid mechanics. So anyway, so this is what you get. So the third equation tells you that the pressure does not depend on Y, depend only on X and T. The second equation can be integrated, tells you that the velocity, it's a Poiseuille flow with that pressure gradient, which we don't know. Right? It's still an unknown. And so I can rewrite that velocity as written here, where U bar is the mean velocity across the channel. And of course, U bar, the mean velocity, is related to the pressure gradient. So this is still my unknown, right? Okay? Other than that, it's just a Poiseuille flow. So the next thing is to go to the equation for T and Y. Now, if A is small, it just tells you that essentially variation in the transverse direction are small, which means that temperature vary primarily along the axis, and in time, variation in the Y direction are small. So T is basically like the mean If you want across the channel, I just denoted this by y bar, rho bar, t bar. And how do you determine this? Well, you go to the next order. Oh, before that, you can, from this, you can determine right away that what V is, because you can, since rho does not depend on y, then from the continuity equation, okay, rho does not depend on y, so you pull it out from here and you integrate dv dy, so you obtain what v is. So you solve for v, and here what it is, okay, or whatever it is. Out of this also come the result that when you evaluate v at the wall, since it has to vanish, you obtain this expression, which is like a continuity equation for the mean velocity u, okay, u bar. This is not a rho u total bar. There should be 2 bars, but I should have put a little space here to see the difference. There is no meaning to rho bar, u bar. Okay. The next thing is, as I said, to determine the temperature and mass fraction. Why? You go to the next order, you substitute into the equation, and as a solvability condition, you obtain the equation, which are essentially what you expect, the energy and the species equation for the mean quantities. So the remaining of the problem is solving this equation with this, right? But this is exactly the one-dimensional problem of a flame propagation, okay? If you assume that the solution is a wave-like that propagate at a speed capital U, as we did when we did a planar flame, then from all the equation in the coordinate xi, which is attached to the flame, render to exactly the one-dimensional problem. In other words, the picture is this. You have a one-dimensional problem here, which is the flame propagating, and that flame is propagating in the tube. And you have a Poiseuille flow here, a Poiseuille flow here, the extent of which we would have to determine in a minute when we treat or when we determine this U bar, okay? But since that's the solution, then we know right away that the mass flux must be -1. Why negative? Because it's propagating to the right. Why 1? Because it's a adiabatic flame mass flux, so the adiabatic flame speed, right? In other words, I know that the solution of this, since I scaled my velocity with respect to the flame speed, then the solution of this should be just the flame speed. So that's what you get, 1. So now that tells you that capital U, which is the propagation speed, is equal to U bar plus T bar, okay? And this is a simple result from here because the rho is 1 over T. This should have been also a rho bar, by the way. Okay, so here is the U bar plus T bar. And now let's look at the 3 cases. Let's look at the flame propagation into a closed end, okay? So flame propagate and the end here is closed. Since the end here is closed, the mean velocity clearly must be 0 because they have to go to 0 at the end. If U bar is 0, it means that, this is the unburned gas, so T bar clearly is 1. Of course, it goes without saying that everything fails when the flame comes very, very close to the wall. Okay, fails meaning that one have to adjust the solution. But we are interested in a sufficiently long tube. We want to know what's happening in most of the region. So clearly there is not going to be suddenly a velocity developing there. So there is some dissipation that occur at the end, or some kind of boundary layer at the end. Okay, so T bar is 1, and from here then you get that U, capital U is 1, which means that the flame propagate as a laminar, at the laminar flame speed towards that end, okay? And actually that makes full sense, and the gas, the burn gas is leaving freely the channel to the left, because the pressure is already adjusted to the ambient pressure, Okay, what happens if you close the right end? The left end. Well, if you close the left end, then U bar must be 0 on that end. But since this is the burn gas, then the temperature T bar must be the adiabatic temperature, which is 1 plus Q. I think here I absorbed the YU into the Q, so that's why you don't see it, but otherwise you can put QYU, it doesn't matter. No, but it is absorbed, otherwise the expression are not going to be correct. And then as a result of this, when you obtain here, you see that the speed is going to be 1 plus Q. Or, oh, by the way, I forgot here to mention in the previous case, since the flame propagated the laminar flame speed, then the position is going to be just given by SL times T, clearly, in dimensional form. Okay, so here it's the burn velocity, so the propagation U is going to be equal to 1 plus Q, or like TA, or in dimensional form, the position is going to be sigma SL times T. Sigma is that density ratio, same thing as written on the blackboard. And this is very similar to what happened, for example, as we shall see later, of a spherical flame that is expanding out, that the flame propagates at a speed sigma times SL. Yeah.
Due to expansion of the gas, of the burnt gas, right?
Yes, yes, absolutely. This is the expansion. So the gas expands, and since the expanded gas can leave freely here, it leaves the channel, and the flame propagates at that speed, at a higher speed.
Why don't we subtract the speed of expansion in the first case?
From what do you want to? What do you? From where do you want?
Doesn't it affect the laminar flame speed?
Well, what I have drawn here is the position. The position of the flame is changing the x dt as sigma SL. In other words, the x dt is not the flame speed, but which we shall define after the break correctly, but it's the propagation speed relative to a fixed coordinate, which is, so that's what it is, okay?
I understand, like, the second case is
Yes.
flame is faster, right?
Flame is faster, right? Due to the expansion.
Yeah, and we...
The gas here expand and they push the flame if you want.
Yeah, we account for it with sigma.
Right, that's where it comes from.
We don't have sigma at all in the first case.
Because the first case is not pushed by the gas. The expansion here is expanded, but it can leave the channel, so it doesn't affect the flame. Right. No, good question. So what happened in the third case when both sides are open? Well, now P has to go to 0 here and here. Remember that U bar was proportional to the pressure gradient, the PdX. So essentially, if you integrate P from 0 to infinity, then the PdX should be 0. So what you have is a Poiseuille flow to the left and a Poiseuille flow to the right. And the solution is not as simple as before, but if you approximate the solution on the left and on the right without worrying about the thin flame, you get this approximation. Otherwise, it's slightly different than that, but I'll show you the numerical solution anyway. The key point here is that the flame accelerates. So the flame doesn't propagate at a constant speed, but accelerate as it propagates through. And you can see here the acceleration. Of course, it depends on the length of the tube and so on. And here are the results of that last case, okay, which were computed numerically. There were some numerical results that needed to be obtained. In particular, look what happened to the pressure gradient. There is a pressure gradient which is built here, and then so there is a pressure gradient on this side and a pressure gradient on this side. One is pushing the unburned gas, the other one is the burned gas. And here is the reaction rate as the flame moves from one position to the right, and then the velocity. What is more interesting is to compare the small a result that I have shown you, where the flame accelerate down the channel with the finite value of a. In other words, now we are no longer assuming that a is very small, but a is like 10 and 5, 10, or very large. Or 5 and 10, those are two values, which means 5 times the flame thickness or 10 times the flame thickness. Note that for 5 times the flame thickness, the asymptotic approximation I used before it's quite good, okay? Otherwise, what you have is a sudden acceleration. In other words, the flame come to a point where it accelerates quite fast. And this can be understood from looking at the pattern of the flow, which you will see here in this figure, but it's a complicated figure, so let me first explain what you see. So at the bottom, you see the color shades is temperature, hot and cold, right? The blue is cold, the red is hot, and the intermediate are essentially where the flame is. The color shade in the top is reaction rate contour. So that illustrates that that's what the shape of the flame would be in this case. And what you see, the white curves here are streamlines, but the bottom one is streamlines relative to the flame, and the top one is streamlines relative to the walls, in other words, in a fixed coordinate system. So relative to the wall, you have a gas expansion here behind at the flame, right? But since the actual velocity due to the friction at the wall is 0, then the expansion is actually going in the y direction, downwards, right? And that's what you see here, right? And in a way, that what causes what we will refer later on as it stretched the flame, and it caused the flame to further accelerate. And so when you see the flame now at a higher condition, it's more highly curved, and that stretching of the flame causes a further acceleration of the flame. And so the flame acceleration that you see here is due essentially to the momentum thrust that result from the frictional forces at the wall, and of course by gas expansion, okay, that tend to further stretch the flame. Okay, so this is the end of this part. Let's take a break, and actually we are more or less on time, so it works.